Yes, there's a lot of different certification exams for solar out there, and there's a lot of crossover on material that could be on one exam and could be on the other. So it's a good idea just to know everything, because if you know everything, that means you're going to pass for sure. The PVIP exam, that's the PV Installation Professional, is the most difficult exam. Here's another exam too, the PV System Inspector. Check it out. Otherwise known as PVSI. So I have a lot of students that take different exams, and for some reason, they ask me questions after the exam. Here's a question. So the rumor goes there was this one particular question, and it goes something like this. What should you look for with 4 different central inverters in the same location? And then there are 4 potential answers, A through D, which are A, 1 grounding electrode conductor, GEC, per inverter bonded and spliced at the main service point. B, 5 grounding electrode conductors, 1 at each inverter and another at the transformer. C, no grounding electrode conductors. And D, 1 grounding electrode conductor irreversibly spliced and connected to the main bonding point at the transformer or main service bus. So this is a topic for the discussion that's going to go on for about 20 minutes. We're going to go on and off of this topic and get into some really interesting stuff about utility scale, solar, and energy storage plants, just talking about this. And also, by the way, if you were taking that test, they might have called that central inverter a central power conditioning unit. How about that? Let's see what Bill Brooks has to say.
If this is a dedicated service for a PV system, and let's say each one of these are 1 megawatt inverters, and they're all coming together to a 4 MVA transformer or something like that, then the transformer is going to have a GEC.
Not the inverters.
Not the inverters.
Yeah. Mm-hmm.
And so that's where they're probably wrong. So I would say A would be correct, is that there'd be 1 GEC irreversibly spliced and connected to the main bonding point in the main service panel, if there is a main service panel, because there may not be. There could be just a connection to the transformer.
How's that going to happen too? Are they going to it'd just be like just for smaller inverters too, right? It's just...
Yeah, so let's say you had a main service switchboard or something like that, some big piece of equipment.
Switch gear that's going to take with overcurrent protection for each inverter.
Right. So then there would be overcurrent protection. In that case, if that was your situation, you have overcurrent protection for each of the 4 inverters at that location. And that service equipment would be connected to the grounding electrode conductor. The individual inverters would not be. The individual inverters are just going to bring their equipment grounding conductor to that point. And if they have a grounded neutral, which most inverters have, then that neutral will be grounded in the main service equipment.
So like on a big power plant too, you might do this like 5-10 times or something, where you have multiple medium voltage transformers.
Right.
For each transformer you have a GEC.
Yeah, each transformer would have a GEC at the transformer pad. And in this case, there might be an inverter pad that has all the inverters and a transformer on it.
And then also where you combine all those transformers, a bigger transformer to go to high voltage.
There may be, or it could just be a switch gear. You know, so if the transformer took you from whatever the voltage is, let's say 690 volts AC or something like that, or 600 volts AC, or even if we have some 1000 volt AC equipment or 800 volt AC equipment, could take you up to 34.5 kV. The whole plant might be a 34.5 kV plant, and in that case, there would just be some large switchgear that would combine multiple 34.5 kV circuits. And then at that point, in most cases, your service is actually at 34.5 kV. It's not at 800 volts or 600 volts or anything like that. It's not a lower voltage service at all. It's a medium voltage service. The medium voltage service is typically have a service disconnecting means that's going to be a 34.5 kV disconnect. And often it could be a recloser, some piece of equipment that has more capabilities than just simply a disconnect. It's got ground fault detection, it's got various things that are built into it and programmed, and it also may have a remote activation that the utility has control over, so that if there is a fault on the system or there's a power outage or whatever, they can activate the recloser remotely and prevent the system from ever even coming on.
So for that, where you're combining all these medium voltage circuits together, you have another GEC there, right?
Well, at that service, there will be some type of a connection. Now, is that where the grounding connection is going to be? It's really going to be up to the utility how they configure their system, because it could be a 3-wire connection, it could be a 4-wire connection to the utility. Different utilities have different circuit configurations, and so depending on their circuit configuration and their grounding requirements, that would all come from the utility. And we would just follow whatever requirements are. And there may not be a grounding conductor at that point, because they may have the neutral. If it's a 4-wire, they may have a neutral, and that neutral is going to be connected to ground at their substation and all, but they may dictate where that connection is made at a service at medium voltage. So the medium voltage services are very, very different than low voltage services that we have for buildings. And so we just go to their guidelines and their rules and we follow those. And then when we get to the secondary of a low voltage transformer from 34.5 down to, let's say, 600 volts or whatever it is, then that connection is not a service grounding electrode connection. That is a separately derived system grounding connection, because now you have galvanic isolation between the 34.5 and the 600 volts. And so just like inside of a building where you go from 480 to 208, 208 side gets separately derived and separately grounded.
Mm-hmm. But you still call it a grounding electrode conductor.
We'll still call it a grounding electrode conductor, but it will not be connected to the main service grounding electrode conductor other than through building steel and things like that.
So let's say you had a really huge solar farm, and then you even had to go 10 miles across somewhere, and that 10 miles was, I guess, your responsibility, not the utility. So you're going high voltage for 10 miles. So for that medium to high voltage, then you're going to have your own grounding electrode conductor.
Well, again, the grounding schemes when we get into medium and high voltage are very, very different. And they're completely dependent upon the utilities circuits and how they set them up at their substations. And so even though the National Electrical Code has information about when you have a grounding electrode conductor, how you would connect it, it doesn't necessarily mandate that those circuits have grounding electrode conductors. And so only if you have a grounded circuit would you have a grounding electrode conductor. That is dictated by the utility first. So we go to the utility first, get the requirements, and then we open up the NEC and say, okay, the utility requires a grounding connection here. Therefore, we need a grounding electrode conductor, because a grounding electrode conductor takes it from the grounding point on the system to earth. And so that's the vehicle, if you will, to get it to earth. And then you have a grounding electrode that is in the earth that we connect to.
So if you were going from medium to high voltage, and then the high voltage 10 miles away is what you're giving to the utility, so the utility would still be interested in your medium voltage that's 10 miles away from where you're connecting to them?
It could. Ultimately, they're going to be concerned about where the offtake point is. And so that point will have to be grounded according to their requirements. What you do on the other end of that line, 10 miles down the road, they're less worried about.
All right.
So the switchgear and all the concerns are going to happen at their service point. And that's typically the way things work, is the utility is focused on their service point, their requirements at that point. Once they take off, it's the engineer's job from there to determine how things are grounded from there on out. And that's going to take the engineering, which then says, okay, if the engineer says you have to ground the low voltage side of that transformer, then you use the National Electrical Code to do that.
And now we have like huge energy storage systems now that are 100 megawatts, 100 megawatt hours in that kind of range. Same type of thing, I guess? Like,
Yep.
Exact same kind of connections and all that?
Exactly, yeah. Because ultimately, these are all inverter-based solutions, 100%. So even though the characteristics of the lithium-ion batteries they're using and all are very different than PV, on the other side of that inverter, their capabilities are virtually identical.
Yeah. So the one thing about PV, though, is it's more spread out than energy storage. So how many megawatts are you going to put on a transformer, like parallel into a medium voltage transformer?
It's a really good question, and I think there's lots of arguments, a lot of different ways on what makes sense. Ultimately, it comes down to cost. transformer costs and the like. We certainly see a lot of large transformers in large PV systems. And so somebody's doing the math on that. But somewhere around probably 4 or 5 MVA would be the largest transformers you see. I mean, occasionally you hear about, I know in China they use stuff up to like 7 MVA and all. You're getting into really, really high fault current capabilities when you get into those units, and so that's problematic. And you're getting really spread out. Even at 1500 volts, those are massive arrays going into those transformers. And so I don't see the real benefit of it personally. But I can't say that I've done 300 calculations on the subject either and said that, oh, this is clearly not cost effective. I think that in the real world, 2 to 4 megawatts or 2 to 4 MVA tends to be the size range that most transformers are in large plants. And then some of those are a single inverter that are in that range to a transformer. And others, certainly string inverters have become a common method and becoming more common. And that's certainly something that I've been working on in my career, is coming up with inverter cluster concepts and things like that, that you can connect directly to the secondary of a transformer without switchgear or anything like that. And that concept, I think, ultimately can get you in a range that's very similar to very large central inverters, but you're dealing with 250 kilowatt inverters that are far easier to maintain and are more likely to have multiple options of replacement. The big problem on large scale PV over the last 10, 15 years is that there's only a couple companies that are still in existence or have been in existence over the last 10 or 15 years. Most of the companies that sell products into that market have been in and out of the large scale market, some of them 2 or 3 times. And so the customer service for those large scale inverters is poor at best, extremely poor. So there are plenty of plants out there where, as the inverters start to fail, they're faced with having to physically remove the inverter or bring in another inverter and set it next to an extremely large inverter because they can no longer get parts for it. That's a horrible situation. And so moving forward, we need to standardize on products that where we have 3 or 4 manufacturers who build very similar products. And then the challenge comes with large scale plants. How are you going to do all your monitoring, data monitoring and things like that? Because a lot of these inverters have data monitoring built into them. So you then have to have monitoring communications protocols that are consistent platform to platform. So you could take one company equipment and remove it and put in its place another manufacturer's equipment, and then it still talks the same protocols and all that. And I think that's ultimately the big challenge with a lot of large scale, is the communications protocols that are involved and making sure that everybody can talk the same language, because we're asking for a lot out of our inverters these days. We're operating the inverters in a very advanced way. We're operating at non-unity power factors, and we're doing all this grid support activities and all this kind of stuff that requires a lot of communication. Whereas the old school dumb, unity power factor inverter, we just plug it in and it's plug and chug kind of thing. That's not the case anymore. So those are the challenges that happen.
So like a container battery, was that like something around half a megawatt?
Yeah, megawatt
like
probably.
That. So if you had a container battery that was a megawatt, so you might fit 4 of those on a transformer?
You could.
So you're cramming those containers together, you're going to have a lot of medium voltage transformers in a smaller area, especially than a PV system.
Oh, absolutely. Yes. If the facility is dedicated to storage, that's going to be a much, much smaller facility. It's going to be more like a substation type of a facility. It's just going to be a glorified substation with storage in it. Essentially, that's what they look like. That being said, I think that the vast majority of new storage projects that are going in are going to actually focus on utility interconnections with solar, because you've already got a utility interconnection built and you've already put the PV generally where it's beneficial to connect to the grid. So these very large plants that are 100 to 500 megawatts in size are all located on transmission lines that have capacity. So if they have capacity during the day, they probably have lots of capacity at night. And so you can use the energy storage to augment the PV during the day if you had cloudy periods or whatever. And you can also use it to dispatch power and source power at night. So you can do both. And so it makes a lot of sense to use these very large PV power plants as energy storage plants, because as you pointed out, there's not a lot of room taken up by the energy storage. And you've got a ready-made interconnection that's already built for however many 100 megawatts that you need. You don't have to build the substation twice, because these substations are very expensive. I think the future over the next 10 years is going to be, I would say, a good portion of these energy storage projects are going to be augmenting PV sites and using that same interconnection.
So if somebody's going to have a big solar farm and they're going to DC couple and put their solar and their energy storage together on the DC side of an inverter, then they're going to have these batteries distributed throughout these huge solar fields, I guess.
You could. Yeah, that's one way to do it.
Is there a different way of doing it? Because
sure. I mean, I'd say most of the storage projects out there that I'm aware of are going in with their own inverters. So
they're AC coupled.
They're all AC coupled systems. And there's good reasons why you might want to do that, because going back to the grid support activities and stuff like that, there may be grid support things that the battery things are doing that the solar doesn't do, and vice versa.
You hear the big DC coupled people that are, in favor of DC coupling say like, well, then you're not clipping your PV and you can get a lot more per inverter and all that stuff.
I mean, those are all arguments for each way. I mean, there's no clear winner in this case. And so anybody who tells you, they're just salespeople. There's great opportunities in the DC coupled world, and there's great opportunities in the AC coupled world. To say that the problem is, if you put all your eggs in the DC coupled world, there's only a few inverters out there that can do that. And very few of them were built with that inverter that has those capabilities. So you're really narrowing your focus on what inverters can even do a DC coupled arrangement with energy storage, because they're all programmed and built for PV. Whereas inverters are fairly inexpensive these days. And so the hardware cost of the inverter relative additional cost to put it onto a battery is not that much. So the savings, I don't think, are magnanimous. Now, if you want to start from day one and build a plant, then DC coupling makes a lot of sense, but it's got to be factored into the whole tariff of the project and everything like that, and how it's being built, because that's ultimately why they're able to sell those projects, is that there's something about the characteristics of solar that don't match well with the tariff that the system is trying to produce power into, and therefore they're having to augment it with energy storage so that they can essentially shift the peak correctly to make more money out of the electrons coming out of the system. And so, projects like Nextracker and other folks, they have these DC coupled options where essentially they can make the plant look like anything they want and essentially load shift their generation from the morning, where it has very little value in the summertime, and shift it all to the late afternoon. And so you dispatch the battery in the late afternoon and evening until it's exhausted, which essentially empties the battery, and in the morning you recharge it with cheap solar power, or solar power that has very little value on the system. You dramatically improve the overall cost or value of the project. But that's because it's all based on what the tariff is that the plant is built on. So
how big are those Nextracker batteries they're using to DC couple with? And Nextracker, of course, can AC and DC couple.
Right, absolutely. So there's different designs. So they're using flow batteries, and the flow batteries that I've personally seen are 20 to 50 kilowatt hours, something like that. And they're essentially dedicated per tracker. So there's a storage unit. That's one of their configurations, is a storage unit per tracker. And then that basically goes through a single inverter that transitions both the solar and the storage. And a lot of the energy during the day actually bypasses the inverter completely, because essentially it's just a DC to DC coupling of the PV and the storage.
Cool. Yeah, I'd imagine that AC coupling is just more future proof because you're going to have however many volts of AC forever, or you have transformers to convert things.
Yeah, the way I like to explain it is the AC power is a common language that everybody speaks. 60 hertz is our common...
Except for Thomas Edison.
Yeah, exactly. And so we speak 60 hertz in the United States. Once you get to 60 hertz, you can go to any voltage you want. That doesn't mean that in DC you can't do the same kind of things. It's just much more specialized equipment. We can essentially order transformers, whatever voltages we want, in any configurations we want, and they're very dumb, simple, and effective pieces of equipment. Whereas a DC coupling activity is more complex because now we're dealing with voltages and differing voltages and making everybody happy and what's the best voltage for lithium ion versus solar, and they're all different. And so the common language of AC makes a lot of sense. And as you point out, there's lots of products that people are going to build for that market. And they're not going to build them just for solar. They're going to build them for the storage market. They're going to build them for the general electrical market and things like that.
Yeah, and by the way, Bill is speaking at 60 cycles per second.
That's right.
So we had to slow this down for all of us normal people so we could understand the genius.
Absolutely.
Yeah.